Assalamu alaikum, meet Ismail, an absolute technology genius.
He'll take you from basic electrical theory straight into real, hands-on builds.
Hit subscribe for weekly explainers and let's start building today.
Welcome to This Explainer. Today, we are popping the hood on our electrical infrastructure. We're going to trace the engineering all the way from the simple direct current sitting in your battery right up to the massive, highly complex power factors that govern our industrial grids. Let's get right into it.
Here is our roadmap for today. We'll cover the basics of current, voltage, and resistance, compare AC and DC current, define what electrical power actually is, unpack active versus reactive power, and finally, look at improving power factor.
All right, Section 1, Basics. Current, voltage, and resistance. We really have to start our journey with the essential cast of characters that make electricity work. Think of voltage as the literal pressure in a water pipe that's pushing the current forward, right? While current is the actual water flowing through it. Resistance acts like a narrowing of that pipe, which causes friction and heat. And Ohm's law beautifully ties all of this together, basically saying that flow depends entirely on the pressure pushing it and the friction holding it back.
Now, this exact relationship is why our houses are wired in parallel. If you wire a room in a series and one bulb pops, well, the circuit breaks and everything goes pitch black. But in a parallel circuit, voltage stays totally constant across all the pathways, so one blowout won't disrupt the rest of your house.
Moving on to Section 2, AC and DC current. Let's see how these fundamentals build into the two major delivery methods that run the world.
So alternating current, or AC, constantly fluctuates and actually crosses zero voltage. That tiny split second at zero is a real game changer because it means a person getting shocked might actually be able to pull their hand away. Meanwhile, DC, direct current, hits with a constant, unyielding, straight line of force. That makes letting go a whole lot harder.
To put that into perspective, the 220-volt AC in our homes operates at 50 Hertz. That means if you get shocked, the current is literally trying to twist and turn your body 50 times in a single second. Your body just cannot move that fast, which is exactly why a shock from a wall outlet feels incredibly jarring.
But, if you're dealing with massive machines, or maybe listening to that famous Salman Khan song from Sultan, you're stepping up to a heavy-duty 440-volt, three-phase supply. This is serious industrial power, meant to drive heavy machinery where your standard household current just wouldn't cut it.
Okay, before we jump into power, I've got a quick challenge to test your knowledge. How exactly do we get the AC power from a wall outlet to smoothly charge the DC battery inside our smartphones? Drop the name of that critical component down in the comments.
Section 3. What is electrical power? Now that we've got our flow and pressure down, let's look at actual consumption.
You see, power is completely locked in by the manufacturer based on what a device is supposed to do. It acts as the direct child of both voltage and current. You can't just magically change a 10-watt bulb into a 100-watt bulb. That rating, measured in watts, is quite simply the voltage multiplied by the current it consumes to do its job.
Now, rotating devices like big motors actually use horsepower instead of watts. So I'd love to know, does anyone out there know the exact conversion rate? Drop your answers below. It's a super fun piece of trivia that brilliantly bridges mechanical and electrical engineering. Section 4. Active and reactive power. This is where standard wiring gets a bit more complicated, and honestly, where the real magic happens. So, if you walk up to a massive industrial generator, the rating slapped on the side is the apparent power, basically the total possible output. But that total gets split into the hard-working active power and the, well, much trickier reactive power. The real question is, how much of that apparent power is actually doing useful work?
Think of it literally like pouring a fresh, icy soda. Resistive loads, like space heaters, drink the pure liquid. That's the active power doing actual, useful work. But inductive loads with coils, like a washing machine motor, whip up a ton of useless foam. That foam takes up valuable space in your electrical grid, but provides absolutely zero benefit. That, my friends, is your reactive power.
Which brings us perfectly to Section 5, improving power factor. Time to fight that useless foam.
Engineers created this brilliant concept called power factor just to measure and balance out this waste. They use capacitors, which are basically the sworn enemies of reactive power, to drink up all that excess foam and bring the whole system back into harmony. By throwing capacitor banks into large industrial zones, engineers neutralize the foam created by thousands of motors, keeping the grid hyper-efficient. Actually, scratch that. It reminds me of a hilarious memory from college. My landlord's son tried to intimidate us engineering students by threatening to calculate our power factor, thinking we were somehow tampering with our meters. It was a totally ridiculous threat because analyzing power factor is literally what we spent all day in class studying. It just goes to show how wildly misunderstood these concepts can be.
Now, scale this way up. On a massive industrial grid, if a transmission line acts too much like a capacitor because of its immense length, it can create very dangerous overvoltage. So we balance it out by adding shunt reactors. It proves that everything in electricity requires perfect opposition to function safely. If a system leans too far toward capacitance, we inject induction, and vice versa. It's just an elegant, continuous dance of physics.
It's this absolutely fascinating balancing act that keeps the modern world running smoothly. And it leaves you wondering, if we could somehow completely eliminate all that reactive foam globally, how much wasted power plant capacity would we instantly free up? It's pretty incredible to think about the hidden power trapped inside our systems. Thank you so much for joining me on this explainer. Keep asking big questions, and I'll catch you next time.